Hey everybody, welcome to another Calc Ready Calculus video. And today we'll actually be doing a fun little calculus exercise, right? So if you guys walked into a class and saw this on the board, what would you think? Because this right here means the second derivative of y with respect to x, and this right here means that the first derivative of y raised to the second power. And the fact that they're equal to each other is false for basically almost every single case, right? But today we'll actually be using some basic integration to find where this case actually does hold true. So first, what I'm gonna do is I'm gonna rewrite the second derivative in this form. So this means we're taking derivative with respect to x of our first derivative. So this right here and this right here means the exact same thing. And then we're just gonna rewrite what's on our right side, dy dx squared. Now I'm gonna do a little substitution, and I'm gonna add z, and I'm gonna say we're gonna say let z is equal to dy dx, to the first derivative. So what's gonna happen is this: we're gonna be taking the derivative of z, and this is just gonna equal to z squared. We're just doing a little substitution right here. Okay, now let's let's do the operation on the left side, right? So taking the derivative of z with respect to x, we get the derivative of z with respect to x, sorry about that, equal to z squared. Okay, perfect, right? And what we can actually do now is we have a separable differential equation. So solving it is going to be relatively simple, right? So what we can do is use separation of variables, bring all the z's to the left side, bring all the x's to the right side. So let's divide both sides by z. So we're going to have 1 over, z squared. 1 over z squared, dz. And then I'm going to multiply dx to the other side. We're treating this notation as a fraction, dx. Okay, perfect. Now let's integrate both sides. Let me rewrite this again so we can use the reverse power rule. Z to the power of -2 dz is equal to the integral of 1 dx. Okay, if we use reverse, I'm gonna keep writing right here. So if we use reverse power rule, we're gonna add 1 to, we're gonna do this. We're gonna add 1 to -2, and this is equal to -1, so we multiply by that. So -1, or just negative, and this simplifies to -1, is equal to the integral of 1, which is with respect to x, which is just x. And whenever we integrate, we have to add a constant, right? You have to add a constant to both sides, but we're just gonna forget about that. We're just gonna add a constant to the right side. So plus constant 1. And the reason we're gonna do constant 1 and not just constant, because there's gonna be a little more constants down the road, so I don't want us to get confused. So yeah, we're gonna have negative z to the power of -1 is equal to x plus our first constant. If we rewrite this, we're gonna have -1 over z is equal to x plus c1. And always keep in mind what our z is. Our z is dy dx. So if we want to find dy dx and then do another integration, we're going to have to solve for z. So we can multiply all sides by the negative. So we're going to have 1 over z is equal to -x. And we could write minus c1, but instead of doing that, I'm going to make a constant number 2, and that's going to be the negative of c1. So here I can just write plus constant 2. Okay. And now I can just put this over 1 and do an algebra trick and just say that z is flip this side. So 1 is equal to -x plus c2. Okay, and now we're going to put in our dy dx again, because our z is equal to what? It's equal to dy dx. So dy dx is equal to 1 over -x plus c2. Okay, this is perfect. So what we can do now is we can integrate again. We have to separate our variables first. So dy is equal to 1 over -x plus c2 dx. So we integrate one more time. And here we have to use u substitution. So let's say u is equal to negative x plus c2. So our du is going to be negative dx. And solving for dx we get dx is equal to negative du. So taking an integral of 1 with taking an integral of 1 dy just gives us y. And then again we were going to rewrite this as 1 over u. Negative comes out and du. So now this is just if we integrate 1 over something, we're going to get 1 over u. So sorry, if we integrate 1 over something, we're going to get the natural log of that something. So we're going to have negative natural log of absolute value of u. Okay, and now if we plug in back what u is, we're going to get that y is equal to the negative natural log of negative x plus our constant number 2. But remember, when we integrate, we have to add another constant. So I'm going to call that c3 plus c3. And this is what we get. Okay, so, let me just rewrite it big right here so you guys can see. Plus c3. Okay. So this is actually a case where if you take the derivative of this expression 2 times, that's going to be equal to the derivative taken the first time to the power of 2. So those two are actually going to be equal. And yeah, this was a fun little exercise. We kept track of all our constants. Obviously, here when we divided by z, we assume that z does not equal to 0. Because if z was equal 0, then this would not work out. So I'm pretty sure this actually means that dy dx cannot be equal to 0. At least using this method. At least if dy dx is equal to 0, then you wouldn't be able to do this whole process, right? Because here you would be dividing by 0. But yeah, this is it. This is the case right here where the second derivative of y with respect to x actually equals to the first derivative of y with respect to x to the power of 2. So yeah, I hope you guys followed through, and I hope to see you in the next calculus video. Bye.